Hi, today we will try to implement the Bleichenbacher attack. What is happening in this attack is we are trying to use a problem in the padding section of the PKCS padding convention, and in the assumption that there is a padding oracle which tells us whether an encrypted message is rightly padded or not, we proceed with the attack. So, what the PKCS standard represents is the initial 2 bytes must be 0002, and then it is followed by a series of random padding, and then there is a byte 00 which is followed by the original message. So once we get a confirmation that a message is according to the PKCS version 1.5 padding, we know that the value of that m will be between 2b 3b minus 1, where b is 2 raised to k minus 16 and k is the number of bits in the representation of n, where n is the modulus of RSA. So using this information, we try to reduce this interval and finally find the message. So this is how the attack proceeds. So initially what we do is we instead of so we know that the encrypted message is the one that must in a real scenario be given to the padding oracle. But since this takes a lot of time, what we are going to simulate here is, instead of giving the encrypted message, we do not go into the encryption decryption scenario at all. So we are working only with the messages and not the ciphertexts. So our oracle is a simulating oracle which takes in the message itself and does not do any kind of decryption before telling us whether the message conforms with the PKCS standard. So what lies ahead is a lot of maths which tries to reduce the interval in which the message might lie in. So for this, what we are doing is we have a different message called m1. m1 is m0 times some value s1 mod n. So we know that this m1 would lie in the interval 2b 3b minus 1. So using this information, we go ahead and try to find a interval for m0. So what happens is we can write m1 as m0 times s1 minus rn for some positive number r, positive integer r. So from this we get the intervals 2b plus rn by s1 and 3b minus 1 plus rn by s1. But the problem here is that we do not know the value of r also. So we derive another interval in which the value of r might fall. So this is done using the information that both m0 and m1 are lying in 2b and 3b minus 1, and that r can be written in the form m0 s1 minus m1 by n. So from these two informations, we find out a new interval in which r might lie. Now, one of the things that we can derive from this interval is that the starting value s1. So initially we said that there would be an s1 with which we would multiply m0 to get m1. So that value of s1 must be greater than n by 3b. So the reason for this is, otherwise the value of r would be less than 0, and we know that less than 1, and we know that the value of r cannot be less than 1 because we have already seen that m1 is m0 s1 minus rn. So this means that m1 equal to m0 s1 would happen and the product would become smaller than it. So we know that this cannot happen, and so we start with an s1 that is greater than n by 3b. Now the next thing is we proceed to find the S1. So this is done using the help of the oracle. We use an oracle. So I will show you the code for the oracle that I have coded. So in the oracle, what we have to check is whether the initial 2 bytes are 0002 and whether there is a 00 somewhere in the rest of the code, but those 00 should not appear in the first 8 bits after the 0002. So after doing all these checks, we return true. If it fails anywhere, we return false. Now we have defined a lot of helper functions also, such as ceil and floor, which gives the ceiling and floor values of the once the division is performed. And after that we have found a value for the modulus, and we have set the value of b as 2 raised to 1008, which will be k minus 16 when k is 128. So when k is 1024. 128 is the byte size. Okay, now we have I have already written down an M0 in which there is a message contained, which we hope to get back. So the M0 starts with 0002 and has a lot of padding, and after a point there is a 00, and after that we have our message. So this conforms to the PKCS standard. Now as I have already stated before, the value of S1 must be n by 3b, and we go on to find the value of S1. So the initial starting value of S1 must be n by 3b, and using that we try to find an S1 that conforms to the PKCS standard with the help of the oracle. Now once we find an S1, we will see what is the next step. After finding the S1, the problem here is once we have an S1, we do not know the values of R. So to find all the values of R, we can use this S1, from which we will get many possible values of R. So using all these possible values of R, we can find different intervals for M0. So using the S1 that we have found and the different values of R that we get using the S1, we find the different intervals if they exist for M0. Maybe M0 might only have one interval. So that depends on the value of many parameters, like the like what we are sending across and the value of n, etc. Okay, so after that what we will do is we will try to find all these possible intervals in which M0 might lie. So we find all those values and we put it into a set. Next what we go on to do is we try to do this for different starting values of the interval for M0. So initially the starting value for M0 that we had taken was 2b plus Rn by S1 and 3b minus 1 plus Rn by S1. So instead of that, what we will do is we will generalize this, and we will let a value a comma b denote a possible interval for M0, and Si note the value of S computed at that step I. So the values are 2b plus Rn by Si and 3b minus 1 plus Rn by Si, and the values for R would then be a Si minus 3b plus 1 by n and b Si minus 2b by n. So using these we will try to converge, or we will try to find whether some new intervals intersect with the interval AB, and using this we try to narrow the generic interval. Now once we get a single interval in which m0 might lie, then what we can do is we can try to find an SI in that interval such that it is the one that we are looking for. So here what we can do is we can pick R's in such a way that the value of the next SI that comes out is twice the one that was before. So to do this, we pick R as this value 2 into b si minus 1 minus 2b by n, from which we obtained values of si which are twice the values of the previous SI. So what this does is this shrinks the interval. Each interval size for step I would be b by si. So once the si becomes 2 times the si minus 1, we are essentially shrinking the interval by 2, which helps us find the required si faster. So this actually models a binary search in which we are reducing the search space by half. So after doing this also, we will try to find an interval such that the upper bound and the lower bound become equal, and we find the exact SI that could give us the exact value of the message we had already sent. So we will see this in the code now. So actually the code has a lot of similarities from the code that has already been given here. The major differences was adding the values for the n, b, and the message to be sent to the, or to the message to be found out. So and also we had to code the oracle, which I have already explained. So now what we will do is we had already seen until finding all the intervals in which m0 might lie using the first SI and the values of R that we got using that value of SI. Now what we will do is, if the number of intervals that we obtained initially was only 1, then we will start doing the binary search kind of shrinking technique, in which finally we will find an SI that suits our match. Otherwise, if the value of or if the number of intervals for m0 is greater than 1, we will again try to find SIs, and we will try to reduce or shrink the number of intervals. So that this is the code for doing that. And finally, when we get a single interval with its initial lower bound equal to its upper bound, we can say that we have exactly found out the value. So I will run this attack right now. So I have put 2 breakpoints, or I have asked the user to give input just to pause the running of the program. So the initial pause is at the here, it is at here. So what we are seeing is the value or the interval in which R might lie. So this is the interval in which R might lie. So we have seen we see 3 values for R. So this means that we must have at least 3 different intervals in which m0 might lie. So that is where the next breakpoint is kept. So where we will print the length of this new m, which is the set of all the intervals in which m0 might lie. So we get three. We see that there are three different intervals in which M0 might lie, and now we proceed to do this pruning technique for by which we will finally aim to find the initial message M0. Okay, so now you can see that there are a lot of messages being printed out, and using that we have finally found the value of or the necessary message. So we can simply compare whether it has been the same thing. This is so the part that we can compare with is 6A736E 6B72. So we see that we have got the same thing after the 00s. So I think we have already completed the attack. So thank you.